Check that. $5. That emote is like perfect. 10 out of 10. Okay, but yeah. This is our final meeting for the reading group. This is kind of where I plan to end it with chapter 4. Do you mean Denise? Son of a bitch! Slim, thank you so much for the raid. I hope your stream was good. I saw you were talking about end simplexes. And then I think you're even talking about like the complex analysis stuff too. But yeah, thank you for the raid. Also, did I say hi to you, Mouse? If I didn't say hi, then hi. Sorry about that. Hi, Joseph. Hi, Fembox. So yeah, today's the final kind of like planned meeting for complex analysis because the plan was just to get through chapter 4, skipping over the stuff without stars, and the last 2 sections have stars. So you just finished eating a banana. Nice. Got to fuel up. You read a Mean Machine Rex tear? Ooh, that sounds fun. Or tarot, I think. Oh, I didn't post the Excalibur link. Let me do that quickly. I normally do that before I start the stream so I don't accidentally show the link. Okay, I think it's time to hop in voice chat anyway too. Let me get that.
Hi.
Hey, Fembox. How's it going?
Oh, doing good. I didn't think I was going to get home in time. I left work kind of late.
Oh, well, I'm glad you made it.
Yeah.
Even had enough spare time to eat a banana too.
Yep. Just snuck one in.
Nice. So this was another like long one for the complex analysis. Like we're able to get through
it. Partly.
Okay. I didn't read it very deeply, but
I skipped around a little and I read most of it and I skipped a little bit.
Yeah, I think like the end of 4.3 seemed kind of optional. Especially that one, but the ideas that we went over here I thought were pretty cool.
The branch point stuff?
Yeah. Or they went over a really like weird one with the square root.
Yeah, I may have skipped that one.
Yeah, I read it, but there were a couple steps I couldn't figure out, and I just didn't stress about it. But yeah, so I guess scrolling through 4.3, they start off by talking about the difference between the Cauchy principal value integral and the more general kind of version, where you have an epsilon and a delta that are varying independently towards a singularity. If you make them both the same number and vary them at the same time, that's like the more restrictive case I think we were talking about in a previous section.
Yeah.
And so at first I was confused about like, if the book is making the claim that these are different things, then why do we care about the Cauchy principal value? But I think the idea is that if you can prove that the first one converges, it must converge to the same thing as the Cauchy principal value. And the Cauchy principal value is easier to work with. So that's how I'm thinking about it. Okay. So yeah, then they started doing stuff with that. It's theorem 4.3.1. The thing with the z minus z naught f of z approaching 0 thing, the meaning of that is kind of lost on me. Like, if you remove the singularity, or like, I guess if it's a simple pole, is what that means. Like, it feels like something related to simple poles, but why don't they just say that if that was true? in that kind of like format for a condition came up a few times later on too.
Yeah, and they said it goes uniformly.
Yeah.
Hmm.
So maybe it's stronger. It's a stronger condition than just being a simple pole. Maybe.
Maybe.
Um, I guess because they do say just the simple pole case. Uh, I was confused about what the phi is here, but I think that's the angle the arc is passing through.
Yeah.
I,
It's
I
in the picture, I think.
oh yeah, okay. Because I was getting confused with like phi of z, the function that is associated with simple poles, but it didn't make sense how they were using it there. So
Oh, I'm only just realizing this theorem here is for small circles. So
uh,
epsilon goes to 0.
yes, epsilon
Yeah,
is like the
I
length of the
hadn't realized
arc,
that
I
before.
guess.
Yeah.
Hmm.
So okay, wait. So B actually part B says something about it's a simple pole.
Yes.
Okay, so I guess part A couldn't be a simple pole then.
I guess not, or at least if it is a simple pole, it's a simple pole plus something else. I don't know.
Right. Yeah, I didn't quite get my head around these theorems.
Me neither.
Part B, I kind of understood it, and I've seen it written in another book where they talk about where they replace that phi with a pi. So instead of 2i pi, it's 1i pi, and that's when you do a small semicircle, I think,
Hmm.
around a simple pole, which kind of makes sense, I guess. If a contour around all the way around a simple pole gave you 2 pi I times the residue, then I guess half a circle would give you 1 pi I times the residue.
I guess so, yeah. Actually, oh, I said before that the arc was going to 0, but it's actually the radius of the circle that's going to 0. The angle is staying the same. You know, it did kind of annoy me that in the figure they use the other kind of epsilon for c sub epsilon, whereas all the other epsilons are like the other kind. It's a really small
Oh,
thing,
yeah.
but yeah.
Yeah.
um,
I like that curly epsilon. That's the one I use.
I think which one I use depends on the
Like the
context.
backwards 3. Oh, okay, yeah.
But there's not really like a particular pattern. It's just however I was taught different things by different people and they prefer different types of epsilon. So yeah, I don't know. This integration of sine ax over x, I thought it was pretty cool that we could integrate that. I never really thought about it. It's kind of weird. It doesn't. I guess it's not an odd function, is it? I was wondering why it wouldn't be 0, but it's not odd. I guess it's even, weirdly.
Oh.
Actually, they even say that later on, I think. They talk about the cosine version being odd. But yeah, they figured out by integrating e to the iax over x. And kind of like the... It's kind of cool I have to put a little dent in the contour to go around the pole at z equals 0.
Yeah.
But it still works for integration over like the real line.
Yeah. Yeah, when you shrink that little dent down to nothing, I guess.
Yeah, exactly.
Oh, this example here I liked. I actually got through it. It took me like a long time.
uh,
I did it a much more complicated way. I found the residues a much more complicated way. I forgot the little trick with the simple poles.
oh yeah, like D prime.
Yep.
Oh yeah, it's kind of wild how many different like this is 6 different integrals for each contour here. Like that notation is
Yeah,
getting a
six
little bit
little
messy,
parts.
but yeah, I guess it's necessary. Yeah, that was a pretty neat thing too. Oh, and this one with the rectangle for the contour, like this reminded me of like a puzzle piece. I thought this was just kind of a fun contour to make. But yeah, the reason for straight lines, I remember figuring out why they chose straight lines at some point. I don't remember now though. It gave some kind of clever simplification. Oh, yeah, just because you can make y equal to a constant if c equals x plus iy, I guess.
Hmm. And we get cotangents.
Yeah, there's another pi cotangent pi, which we had in the last section too, or maybe chapter 3 or something with the Mittag Leffler.
Yeah, yeah.
Um, then we get a similar version of, I think, the theorem from before.
Yeah, except now we're going to infinity instead of going to 0. So it's like a big
Yeah.
circle instead of a little circle.
And does the other one require being closed
I think that other one was
into
just
C
a
epsilon?
segment of arc.
Oh, yeah.
I was unsure about that because
Oh, is it
in that
just the
picture
arc and
you're
not the
looking at,
connecting bits?
I don't know. I think maybe it is just the arc.
Yeah, I only see the arrow on that piece. Okay.
But what does it say? It says suppose on the contour C epsilon, right? Does a contour doesn't have to be closed, right?
No,
And they
no.
don't have the circles on the integral sign.
Oh, true. Yeah, it's I don't think I ever realized that then. It's only the arc and not the, I guess, two like radii connecting it.
Yeah, I think so.
Mittag Leffler is a nice museum slash library in Sweden. Really?
This must be Googled. Oh, it's one dude. I thought it was two dudes.
It. I thought it was 2 dudes too. Is it not 2 dudes?
I think it's one.
The Royal Swedish Academy of Sciences. Uh. Wait, you can get it. Mittag Leffler like merch.
Why not?
Like, well, they have like a Swiss Army knife. That's kind of crazy. Um, so wait, like, who the heck is Mittag Leffler? It is one dude with a hyphenated name. Huh. And yeah, I don't know of many Swedish mathematicians. So maybe that's why he has a museum and library. It's a nice little fact, Puika. Thank you. Rumor says Nobel's wife cheated on him with Mittag, and that's why there's no Nobel Prize for math, but of course it's a myth. Really? That's kind of crazy. I wonder if the Wikipedia page says that.
Well, he's pretty handsome. You could imagine, women flocking around him, I think.
He has a very
Yeah.
bushy mustache, I guess. I don't know. Maybe women are into that.
But look at the way he's looking at you through the spectacles. It's
Oh,
like,
that's true.
yeah.
That is quite the look. He had some involvement with the Nobel Prize Committee. The Wikipedia page doesn't say that exact rumor, though. Never the truth can wave a good story, true Slim. Okay, the camera. No, I don't think I can pull that off. The glasses would really help sell it.
And the mustache, you got to start growing it out.
Yeah, it looks really long. I'm not a fan of his hair though. Like, I think his hair is a problem.
Acta Mathematica.
Huh. Interesting. And we need to do like a mathematician like power ranking, but based only on looks. It'd be funny. But okay, yeah. When it comes to that other theorem, I think you're right. It's just the difference between the radius going to 0 or infinity. Maruf, I'm American. And they use this kind of funny example of integrating a function that's really not that hard to integrate with real numbers.
Yeah.
But it uses a unique, pretty cool like contour, which I guess is probably why they chose it.
Yeah, when they threw that logarithm in there, I was like, where the heck did they pull that from?
Yeah, that's kind of, I don't know who figured that out.
Yeah, wasn't that clever? That was so clever.
Yeah, because I think like you throw it in there specifically because it has that branch cut, and that's helpful.
Yeah, because you're trying to go from 0 to infinity. So that's exactly where you want the branch cut, so that when you go different ways along that branch, they don't cancel out. They wait, am I right? Or do they cancel out? No, they don't, because one of them is on the 0 and the other one's on the 2 pi or whatever.
Right.
Yeah. Yeah, cool. Yeah, you got to look at that horseshoe magnet shapes, or the Pac-Man shaped contour with the closed Pac-Man with the closed mouth, but the Pac-Man's top lip is like a 2 pi eye above the Pac-Man's. He's got like an overbite or something, right?
Pac-Man with an overbite.
Or maybe he's got an underbite, something like that.
Honestly, this would remind me of one of the E&M problems that we did when we learned about conductors. And we had to look at some weird shapes for like how they could look.
Oh yeah.
There's
I
one
forgot.
one that was like really like challenging with that. It looked like a circular maze with a hole in it.
Yeah, I like this. This example was cool.
Yeah. When I was first reading it, like how they got the last equality on page 246 kind of was throwing me off. It took me a while to realize that's just from the residues and was a separate
That's the residues.
calculation.
Same here. Same
Yeah.
here. I was like, how'd they turn this into this? Like, what happened? And I'm like, and later I realized, oh no, that's the residues right there.
Yeah.
Yeah.
Hey, Skirtle. Um,
Now, the
yeah.
one thing they didn't do in this example, which I thought they should have been careful about, is what if A equals B? Because they didn't say A could not be equal to B.
And that would make it a double pull, is what you're saying? Like that's what the issue would be?
Yeah, and I think you have to. I think that in that case you have to do it a different way.
I guess with that, I think that'll just change your residues, right? Otherwise, you'd be fine.
Yeah, maybe you're right. The only reason I noticed that is because I did it the long way. I did it the old way, without complex analysis, and and you get a pretty different answer. I think you just get like -1 over A or something like that, or -1 over A, -1 over B, whatever. -1 over the number.
Yeah, I wonder if that would also affect the circular arcs, whether they go to 0. Not sure.
Maybe it would work. Maybe you're right. Maybe it would work. Because if it's a double pole, then the residue would be different, right? Yeah.
Actually, with the very last answer they get, there's a like 1 over B minus A. So I think they're just probably not addressing the A equals B case.
Yeah. No, they didn't.
Well,
That's fine.
not really.
They're probably just assuming A and B are different. They just never stated it.
Yeah. Yeah. And then we do log squared over x squared plus 1. But it's a similar trick, it looks like. This one you actually do need complex numbers for, at least. It's not like a simple thing you could do in Calc 2.
Right.
Um... Oh yeah, okay, and then with the x to the m minus 1 over x squared plus 1, I was so confused why they had it to be m minus 1 and not just m. But it's one of those things where they know what the final answer is going to be, and it looks slightly cleaner if you make it m minus 1.
Oh.
I also didn't realize... Actually, oh wait, I got a little weirded out by the idea of branch cuts for just like a z to a power, but I guess because there's fractional powers in there.
So m doesn't have to be an integer, obviously, I guess. Yeah.
Yeah.
Because then the only integer between 0 and 2 would be 1, and then it would be a pretty boring problem.
Oh yeah, it'd just be
Okay.
a U sub, yeah.
Oh,
Hey,
yeah, sneaky. Yeah, so when you have fractional powers, you have to think about branches.
yeah. It is cool that they were able to use the same contour though, as they did with another problem. I'm pretty sure it was the same one. Yeah. As with the first one they did with the keyhole.
The Pac-Man.
Yeah. Um, and then this is where they got a weird like ninja looking thing with the more
Oh my
complicated
God.
branch
I,
cuts.
by this point, I think I had moved on to the next section. I didn't look at
Okay.
this one.
Yeah, this is one where I really kind of fell off the rails. There's a couple things they did in here that I just didn't get.
Oh, this is the square root one you were talking about.
Yeah.
Hmm.
Um, and I didn't understand at all their justification for like putting z squared minus 1 to the 1/2 in polar form, or how they got like the different like how z squared minus 1 to the 1/2 is similar to x squared minus 1 to the 1/2 depending on the choice of branch cut. I didn't understand that either.
Wow, what
But
are they doing?
yeah, it I never read 2.3, so I wonder if they explain it a bit better there.
Did we skip 2.3? Was that
It was a
optional?
starred one, yeah.
Oh, okay. Oh, it's probably that was more to do with like branch cuts and stuff, wasn't it?
Yeah,
I think that was where they talked about like if you had two branch points, you could connect them with a line and you didn't have to go out to infinity.
I think so, yeah.
Okay.
Um, yeah, that's when
Boy,
I
it's
didn't
really
stress
cool.
about it too much.
Yeah, it looks complicated, doesn't it?
Yeah, it is.
It's still going. Wow.
Okay, finally it ends. Yeah. Okay. See, that was it for 4.3. Then 4.4. We get the argument principle. Uh, what is fx inverse of Dawn? Nod, maybe? Exactly 0.1. Okay. I'll take it, I guess. I don't know what that means. Um, a fractional Laplace transform? I don't know what that would mean. I'll scroll through it quickly, but I want to stay on topic to the extent I can. That's a lot of Fourier.
Ooh.
I don't know where the fraction would be in that.
Wow, that stuff does look cool.
Yeah.
I had to learn some of that when I took a course in signals.
Oh, I guess yeah. That would help.
Although honestly, the teacher skipped a lot of the math, a lot of the like proofs of like the math, and we would just use tables, to do the transforms and the inverse transforms.
Oh yeah,
But the
yeah.
book talked about it a little bit, and I tried to read it, but it was kind of complicated.
Yeah, the it's not easy. So yeah, Papadori. I'm not sure offhand if there's like such a thing as a fractional one. I'm not sure exactly like the fractional part would be.
What's the definition of Laplace transform again? E to the, oh, I see.
I
You
think it's
multiply
that
by
right
e to
there.
the,
Yeah.
yeah. Fractional transform.
Maybe you're like rooting the f of x or something. Oh wait, I guess the Laplace transform is actually 4.5.27. But I still don't see where the fractional part would be. Yeah, who knows?
Hmm.
Um, yeah, so back to the argument principle. It's kind of cool how it can give you the number of zeros in poles. And I read the
It's like,
proof, but it was kind of weird. Yeah, I still don't quite understand it. Sorry, what?
yeah, it's amazing. I think it's amazing.
Yeah. Your brother asked about fractional derivatives also. Oh, nice. Those I have heard of. You two both seem like pretty curious people, I guess. With a lot of like difficult math questions. Um and they gave another interpretation of that with the winding number stuff. Um Oh, you know what? This thing is like a sneaky log. Like
Is there?
the result of the integral, like you could do a u sub with this and you'll get log of f of z.
Oh, f prime over f. Oh.
So yeah, I that's probably where the winding numbers part comes in. With like the
Oh, and every time you spin around 1 through 1/8 through 360, you go up by 2 pi I, don't you?
yeah.
Your
It's that's why they divide it back out to get the actual number of like the actual like winding number, I guess.
hmm. Okay.
Oh yeah, okay, and then they gave this different version of it for where you have f prime over f, but now multiplied by another function h. But now they switched to saying like before they're using n to mean zeros, and now they're using z to mean zeros, and I really hate this like z I z. Like, this is terrible. The first z is a variable, the second z is shorthand for a zero.
Hmm.
I wish I just stuck with n, but yeah, I had to look at that for a while to before I could figure out what this meant. I guess they already use n also though, so this is like this is bad for multiple reasons. Okay, and then for example 4.4.1, there's another pi cotangent pi, and the contour
Yeah.
they're using here is kind of wild, but I can see where it would come from. They used the same type of box contour for cotangent previously, and then you just make two cutouts for the two other singularities. Um, yeah, I don't think I quite understood where they got all this from. They just kind of cut straight to the answer, and I don't think I quite followed how.
I guess right there they're saying those were simple poles again.
Yeah. But yeah, I don't know. This example was a little bit weird. The next one, though, was pretty neat. With finding the number of zeros for z cubed plus 1.
Yeah. How did they do this?
They chose a contour that's like a semicircle in the first quadrant. The entire thing, not just the arc.
Mm.
And then what? Oh yeah, so they're trying to figure out the argument to get the other side of the formula because they know there's no poles. And so as long as you can figure out how many times, or like, you know, with kind of like the input contour being just a quarter of a circle, under the mapping z cubed plus 1, how many times does that wind around the origin? Is what they're basically trying to count. The argument was like, it's not as easy as you would hope it is, though. But they basically found that it just winds around once.
What does it wind around?
Uh, I was just assuming the origin, I guess. Because it wouldn't have to be. Basically, it's really just the change in argument of the contour. Maybe bringing in the idea of winding number isn't the best for this example. Like, I think the basic idea is you start with that quarter circle, and you just, that's an argument of pi over 2. You apply the mapping to it and figure out what the new argument is.
Yeah, because that quarter circle's in our z space, and we have to map it to our w space or whatever.
Yeah.
And what was the map? It was z cubed plus 1.
Yes.
Oh, so all right.
So they figure out that like the bottom part of the arc along the x-axis kind of stays put, and then the straight part on the y-axis gets rotated around by 3 pi over 2, so it comes back around to the x-axis to form like one complete revolution.
Crazy.
Yeah, the way they actually worked this out was kind of difficult, but like intuitively I can get that they basically just took the angle and multiplied it by 3, and they found that this quarter circle gets mapped to an entire circle. So that's why you get 1 for the 1 over 2 pi times the argument. Yeah, they talk about like cotangent or just tangent and like, yeah. And figuring out what quadrant it's in. Yeah, it was a little bit weird.
So, okay. So what we're doing is we're taking that quarter circle, and we're imagining as we like walk around that quarter circle, as the point traverses that quarter circle counterclockwise, we're trying to imagine, we're trying to work out what the image, like the functional image of that point is doing in W space. And
Right.
you're saying like if we were able to think about that point in W space as it went around, whatever it does, it spins once. It spins once. It goes through one loop somehow.
Yeah, if you travel a small amount in the z space, like through a small angle, that angle gets tripled in the W space. So by the
Yeah.
time in the z space you get up to the y-axis in the W space, you've gone all the way around.
Wouldn't we have gone 3/4 of the way around?
Uh, yeah, but we started at pi over 2 for the, like, I imagine like we're taking that vertical line on the y-axis and like rotating that around by 3 pi over 2. Well, the argument that I said before doesn't quite match with that. No, yeah, that wasn't a good explanation that I just said. Because you're right.
We want to cube it and add 1, right? That's what we're trying to, that's what our function's doing. Cubing and then adding 1.
Yes.
Feels like the adding 1's not going to do much unless we're close to 0. Like once we let that circle go out to infinity, the +1's not going to do much.
Yeah, they kind of like
So
they
it feels
use some
like
like
the circular
asymptotic arguments to deal with the one. Yeah.
Yeah. It feels like the circular arc would become, instead of quarter of a big circle, it'd become 3/4 of a big circle.
Well, I thought I understood this, and now I don't.
Sorry.
So yeah, no, this is a. Well, no, I had the wrong understanding, so this is a good thing.
On the real axis, z is x, f of xy is x cubed plus 1, positive continuous. Hence, set x equals capital R, y equals 0. The angle is 0. Yeah, I mean, that makes sense. But if you're on the real axis and you cube and add 1, you're still on the real axis, aren't you? So that part on the real axis is going to stay basically, like you said, it basically kind of stays where it is.
Yeah.
And next we follow the arg fxy around the circular contour. For large R, arg of fz is basically 3 theta. Yeah, we basically tripled it. At z equals IR, so now we're up to the y-axis.
Yes.
Theta equals pi over 2. Hence the argument becomes 3 pi over 2. Okay, now what about the imaginary axis? What happens? If we cube that, it's instead of plus I, it's going to be like minus I.
Mm-hmm.
But now what about this +1? Is that going to be a problem? As y traverses from infinity to 0 from above, the tangent goes from minus infinity to 0 from below.
And tangent phi is imaginary of f over real of f. So, well, that's confusing because the real part of f is 0, is it not? Well, I guess the 1 saves it.
Oh, the +1 saves it. Oh, yeah, I get it. So it's not division by 0 there. Maybe that's why they put no.
Okay, yeah. And so then if y is going from infinity to 0 from above, the imaginary part has a negative sign in front. So it's going from minus infinity to 0 from below.
Yeah, I mean, okay, I pretty much get it. It's basically been reflected because we cubed it.
And that somehow means that phi goes from 3 pi over 2 to 2 pi.
Oh,
I think they're talking about like the actual graph of tangent.
yeah, probably.
And like tangent of 2 pi is a 0? Or is that an undefined?
Yeah. I think it's 0.
Yeah. Oh, okay.
Okay. I don't quite understand how they calculated that. They're keeping like a running total of the angle, aren't they? I didn't quite get it, but I understand the idea, I guess.
Yeah. Um, I feel like there should be some type of easier argument, or if you plug in something on the imaginary axis, you should be able to get something that comes back around to the real, but I don't really see it. I guess maybe that doesn't happen. You know what? I guess it kind of does. Like, if you look at the f of xy equals minus iy cubed plus 1, as
Yeah.
y goes to 0, we are approaching just the real number 1 from
Yeah.
below. But
Yeah. Okay.
yeah, this is a lot more subtle than I thought it was. BR gaming sign integrates to cosine or negative cosine.
Hmm.
God, okay. What a weird. Okay, this that argument was a lot harder than I thought it was. But and certainly they find the total change in argument is 2 pi, so you just get
Yeah.
1. And since there's no poles, that must be a 0.
Okay.
Um, then we get, I don't know how you pronounce it, Ruche.
Look what they said. As we have seen. Wait, just scroll up one more line there. As we have
Uh,
seen, one must calculate the number of changes of sign in imaginary fxy and real fxy in order to compute arg fxy. Yeah, that's kind of what they were doing, right?
I guess that's like an intermediate value theorem, but 2-dimensional, I guess. And each time you pass through one of those axes, you get another pi over 2.
Hmm. All right.
Interesting.
Yeah, I'm going to struggle with that.
Yeah, same. All right. Ruche, I guess, is how. Or I don't know, Ruche. I'm saying
Yeah,
Ruche in my head. I don't know.
let's just say Ruche, I guess.
Ruche, okay.
Is it a French guy?
It seems French. I don't know. uh, yeah, well, FG,
Well, if they're going to put that mark on the e, we better say Ruche. But I
that's
don't know.
true. Yeah.
Mm.
Let f and g be analog on inside a simple closed contour C. If the modulus of f is greater than mod of g, then f of z and f of z plus g of z have the same number of zeros on the contour C. In the contour C. This one seems like very strange, but it actually does become pretty helpful from the examples. Like it seems a little bit like random.
Yeah.
Um, but it's pretty neat how you can use it to prove the fundamental theorem of algebra. It didn't quite follow what they're doing with the step with r is greater than maximum of that stuff. Hey, color cone. But yeah, the actual example with playing around with what f and g are, depending on the region, I kind of liked.
Hmm.
The proof for the fundamental theorem of algebra, I didn't really get it. But... Oh, you know what? Color cone. Do you know if it's Ruche or like something at least like a little bit like that? We're just debating how to pronounce it. Yeah, close. Okay, I'll take close when it comes to French sounding things. um. Yeah, so they apply it to polynomial, and they also apply it to a more difficult function that you couldn't do with other methods.
Hmm.
So it seems like a pretty helpful thing.
Yep.
All right, you want to get into problems?
Yeah, queue one up. I'm just gonna give me 1 minute. I'm gonna fill up my water bottle here.
Okay, sure. Okay, going back to 4.3. I don't know why I'm doing it there. Explain now that the reading groups are winding down. Uh, I'm not planning to replace them with anything. I just want to have my free time, to be honest. This has been a lot of studying. And I'm gonna go and I'm planning to like independently study some random things, and not do a full on like group form or anything. I'm retiring. No. Use principal value integrals to show this integral is equal to that, where k and m are real. Note the function e to the I kz minus e to the I mz over z squared as a simple pole of the origin.
Oh wow, you went to dark mode.
Yeah. So,
On my screen, it's white. It's light mode.
yeah. So it's kind of cool. You can toggle it on your end.
How do I change it?
In the upper left little hamburger menu, at the bottom there's theme.
Okay.
So sun is light mode. What's this third one? Oh, it's just like system mode. Okay.
Ooh, cool. Actually, on my screen, I'm watching your stream, and you've got a white background behind the image. But on mine, the text went white and the background went black.
What? Huh.
I'm not kidding.
That's weird.
Yeah, I don't know. It just did.
I don't know how that works. Okay. Yeah, Slim, I figured out that I had hardware acceleration turned off because Twitch had a period of time where it didn't work well with it, so I just turned it back on. Oh, you are being asked by Poison Mouse what 1 + 1 is. I don't know why, but
What's 1 + 1? I'll get back to you, Mouse.
Yeah, I can imagine that one's gonna take some work. Use your fingers. Okay, so we're going from 0 to infinity. This isn't... Ooh, it's even. Okay. I
Are we
bet.
doing? Oh, we're doing part A. Yeah, yeah.
Yes, from 4.3. Um,
Oh, they told us what the answer is. That's good. We got to shoot for this.
yeah, it's kind. Um, since they were nice and gave us an even function, I bet they want us to do like 1/2 of the integral from minus infinity to infinity.
Nice.
Oh, yeah, and we're replacing the cosines with z's. With e's.
Ooh, you did it right.
I did?
Yep. When I was doing one the other day, I changed this into e to the kz instead of e to the ikz.
Oh, no.
And
Do
you
I-
know what? You basically get the same residue, except it's like multiplied. It's divided by I or something.
Oh. Yeah, I don't know what
I
the
mean, I
significance
went
of the
back
I
and
is.
fixed it, but all I had to do was like add an extra I on my residues.
That's kind of weird. Yeah, I never really questioned why that looks the way that it does.
Yeah.
Okay, so we have a double pole at z
Yeah.
equals
Why is
0.
that? Oh, I know why it is, I think. Because when you take this e to the ikz and e to the imz, when you let z become real, yeah, when you let the y component of your z's go to 0, right? It turns into e to the ikz, which is like cosine z. Sorry, e to the ikx, which is like cosine kx. Because we're trying to find a cosine, aren't we? Or we're trying to find a cosine of x. So I guess we want the x to be the one that sticks around when we're on the real axis. I don't know if that makes sense. Because when I did it without the I, you know what I got? I got the y was sticking around and the x was going away. Yeah.
Hmm. Okay, I don't know what's happening in chat. But no, so I'm planning to do a little bit more like complex analysis stuff independently, and then some like differential equations review. Oop, I can't use CR twice.
Ooh, differential equations, you say?
Yeah, I want to learn the
Nice.
actual proof for like existence and uniqueness and like remember
Oh, no.
systems. You don't like that?
I don't like the proof of existence and uniqueness. No, I like the systems. That sounds fun.
Okay. I don't know, like maybe I can organize like a one-off stream on it or something, but I don't want to like do anything too like big anymore. Tuesdays will just be normal math help.
Okay, so let me see what you did here. You just drew some kind of a contour here.
Yes, this is a contour that they've kind of been drawing.
Oh, because we've got like a. So what do we got? When x is 0, we've got a. Is that like a double pole?
Yeah. Wait, why are they saying a simple pole? Oh, because the e's on top cancel one of the c's? Is that it? They say it's simple pole.
Oh. Yeah, because cosine 0 minus cosine 0 is 0, isn't it? On top. So I guess one of them does cancel out kind of when you go to 0.
Huh.
Yeah, that seems good.
Okay, yeah, I could see the power series argument for it, I think. But like it's the same true with e's. I guess it is.
I was just thinking of L'Hopital.
Okay. So we're gonna have 4 integrals here. How are they? I'm checking the book for how they're doing this notation again.
I was calling it like CR and CE. Yeah, that's what you called it too.
Okay.
And then on the picture you can show, let's see. Yeah, this is R here. Oops. That's R, that's minus R. And that's E, and that's minus E. So we got to take one. Yeah.
yeah, we're getting like a double limit then because we want E to go to 0. No, they're using like some A intermediate point in their example. Huh.
Yeah, I think you're good. You can just do those 4, like 2 semicircles and 2 line segments.
Oh, yeah, okay, because then they fix it up at the end. Okay, so if I do say like C1 first, that's going from minus R to minus epsilon. And then like C2 is going from epsilon to R. And here we would have just the z's would become x's because it's just a real. We're on the real axis. And then plus oh, their notation is a little bit different. They do parentheses like that. Max is so real, it's unreal asyntax. Now the 2 circular arcs, which they don't bother parameterizing that, at least in this stage. Oops, what am I writing? In that you have to keep, actually they do it separately. C epsilon, and then the same function with z. Oh no. One more integral. BR gaming, not right now, no. Okay, and so hopefully we can use one of the theorems from the chapter to prove the second 2 integrals are 0. Or something easy to calculate, maybe. It should be that first theorem with the A and B that we were looking at. Okay, yeah, part B, because there's a simple pole, maybe.
Ah, okay.
So it's I phi times the residue for counterclockwise. And so the residue, the n over d thing, I guess would apply here. because they say it's a simple pole, which I definitely would not have thought that on my own, but so the numerator stays the same.
We're going to get 0 over 0.
Oh.
Can we L'Hopital?
I mean, it's just evaluating it. They didn't say anything about taking the limit. I we probably would have to simplify it first before we can use those, maybe.
What about if we just expand out the exponentials?
I think we'd
Taylor's
have
series.
to. Yeah.
That might work.
Because we got to get rid of some of these z's. I'm blanking on the series. Something over n factorial. So whatever's inside the parentheses, I guess.
So the n power, yeah. Yeah, that's it. IKZ to the n over n factorial.
Actually, maybe it's better to write out the first few terms than doing the summation version.
Oh, yeah. Yeah, let's do that. I like that.
So it always starts with a 1.
Because we only want the residue, so we only have to go as far as the q. We have to get the linear one, don't we? Because it's over z squared.
Yeah, I'll go out to the next one out just for fun, but...
Okay.
I am not putting my dot dot dots. So yeah, so the point is that the ones cancel, which allows us to remove a z from everything.
I think this here should still be z squared.
Well, I was doing the n over d prime thing.
Yeah. Yeah.
Oh, maybe
but
we
this is
shouldn't
two
do that
different
yet.
ways. Yeah, I feel like this is two different ways to do it.
Yeah, maybe we should do the simplification thing first and then worry about n over d. So I wonder if that's premature to use it like right now. Okay. I don't know.
Yeah, because I think the residue is going to come from these two, isn't it? These linear ones over the square.
I guess they will, yeah. Okay. And then the residue of that at 0. Now we do the... Oh, wait. No, it's going to come from the squared terms. Because, never mind. It's coming from the linear terms. Is equal to ik minus im. Because we plug in z equals 0, take the derivative of the bottom. Okay. And so the point of this was to say that... Oh, wait. I'm wondering about my 1/2 now.
Yeah, the 1/2 looks good.
It's okay? Okay.
And then we have to multiply this residue times I pi, don't we? Or is it minus I pi maybe, because we're going the wrong way around?
Well, the epsilon one gets a minus sign. The R is fine.
Yeah, I'm just thinking about that epsilon one for now.
Okay. Yeah, that's gonna get a minus I pi times the residue. But so if R is gonna be the exact same thing though, isn't it? So these are gonna cancel. But
the R is different because the R is going out to infinity. So.
Oh, we can't use the
what
one
happens
that
when we
have to use the other theorem maybe?
Yeah.
I mean, part B doesn't say that epsilon is going to 0 though. What is the other theorem?
You mean part B of theorem 431?
Yeah.
Oh. I think it did say that though.
Only part A says it.
They both have limit epsilon goes to 0.
Am I blind? Oh, never mind, you're right. Okay, that's probably a bad theorem to use then. We should use the other one. So yeah, if R is going to... So theorem 4.3.2, when R is going to infinity, z f of z approaches 0 uniformly.
Oh, yeah. Oh, it does. Doesn't it? Wait, no.
So the z in front serves to multiply out the z in the denominator. I mean, if the numerator, if we put that back into a series, is that what we need to do?
If you replace z, if we let z be x plus iy, then e to the ikz is e to the ikx times e to the minus y. Okay. That sounds good to me. Yes.
Wait,
that sounds good to me.
Following.
So e to the ikz, right?
E to the ikz, yep.
If we think of z as x plus iy, here, let me write this down underneath the little picture
here. Okay.
So e to the ikz, e to the ik x plus iy, which is e to the minus ky, right? E to the minus ky times e to the ikx, where x and y are real numbers, right? So this thing has magnitude 1. That's on the unit circle.
Oh.
And this thing, if we're in the upper, okay, what about k though? What can we say about k? Did we know that k was just a real number, right?
Well, e to the minus ky is r, right? Well, that doesn't make sense.
Oh, is it?
I mean, it is, but then it doesn't give us for there's something that's weird about this still. But like, since the other part has magnitude 1, that means this part in front is just the magnitude of e to the ikz.
Oh,
I just undid something.
yeah,
I
you're
don't know
right.
what I did.
You're right. If this is magnitude 1, then this thing has to be the magnitude of. It has to be the radius, right?
Yeah, I'm still trying to work out how that's a helpful thing though.
Yeah. Wait. I don't want that to be true. Wait a
Yeah.
second. Yeah. No. No. Z. No. Wait. Actually, Z. The magnitude of Z is R. Right. If you're on that circle, the magnitude
Mm.
of Z is R. But e to the minus ky is a different number. Maybe we got to do this because you know what I noticed? We're getting things in terms of k minus m, but in the answer they said absolute k minus absolute m. So maybe we want to let this be the absolute value of k. Anyway, what I'm trying to say is if I knew that k times y was positive, right? Then e to the minus ky is less than or equal to 1, right?
Yeah.
And then this whole thing is small. This whole thing is small then.
Okay.
And I can do the same thing for e to the imz, right? I can bound them, is what I'm trying to say. And if I can bound them, then their difference divided by z is definitely going to 0 as the radius goes to infinity.
Okay. I think I like that, yeah.
Yeah, so I'm trying to. I don't really know how to argue this, but I'm trying to bound these things.
I guess I'm kind of thinking about it like, if R is going to infinity, Y is getting potentially very large. And just kind of,
Yeah, y is for sure. Yeah, y is getting large. That's why I want ky to be negative, right? Or ky to be positive here,
yeah.
because then I can bound this thing.
See, Y is always positive for the contour that we chose. Or 0,
Yeah,
I
and so
guess.
if I could make sure k was positive as well, then we'd be good.
Yeah.
So
And if K was negative, we just flip the contour to the bottom. And I think we'd be in business
oh
again.
yeah, you got it. Oh, of course, there you go. Because we took the upper contour. That means k has to be positive. Yes, if k is negative, we flip it upside down, and then we're good. I love it. That's a good way
Nice.
to think about it. Okay, so doesn't that mean that this final one here that you were just about to do, this has to go to 0, right? Do we agree?
Yes.
Okay, so and what else do we know?
So this is nearly the pi over 2 k minus m that we want. I guess we want a minus pi k over m. But
And don't we still have to say that this initial setup that we had was 0, don't we? Uh, wait, is that true? Yeah, because it's a closed contour and its interior has no poles, right?
oh, true. Yeah, the entire thing's equal to 0.
Yeah, okay, good. So the entire thing was 0, and we've split it up into pieces. And one of the pieces is the integral we're looking for on the real axis. And the other piece is this residue thing that we came up with. So we're getting close.
Um,
So what do we have to do? Take the
it's equal
imaginary
to
part? Oh, no,
0.
you already got I times I. Okay.
Like, we nearly have the exact thing that we want. Like, if we just take stock of where things are now the dust has settled, we have from minus r to minus epsilon, plus from epsilon to r, I'm just going to say f of x dx,
Okay.
plus pi over 2 k minus m equals 0. I mean,
So you subtract it over.
We still have the 1/2 over here. That's going to kind of ruin it, though.
Oh.
And so I wonder if we need to... we probably can't evaluate one of the integrals.
Wait a second. Maybe don't put all these 1/2s on here yet. Is that gonna?
Yeah.
That won't. Would that change anything? I don't know if that changes anything.
Um.
Could still be out by 2, right?
Oh, well, maybe...
Oh no! Wait.
Yeah, I think that maybe does fix it.
Yeah, something was wrong with the 1/2 somehow. I don't know why.
Yeah, like my gut was telling me before that something wasn't quite right with these, but I think only certain ones should have got multiplied by 1/2. But what we can do is we can say that this integral is basically the minus infinity to infinity along the real.
Yeah. As epsilon goes to 0 and as r goes to infinity, this goes to negative infinity to infinity.
Yeah. Is equal to pi. I'm not worrying about the absolute values right now, I guess.
Minus pi.
Yes, thank you. And then we use an argument of the function being even to justify saying from 0 to infinity.
Nice.
That is 1/2. Hard locked. Let's math. We're doing well, dude. Oof. Okay, so how do we justify the absolute value bit?
Well, I think if k and m, or so if k and m are positive, we're good, right?
Right.
And we just said if k was negative, we were going to flip our contour upside down and yeah, okay, I see what
Hey,
you're
what if
saying, but how do
there's one of each though? Hey, Wizard of Datums, welcome in.
well,
Is that the meth the kids talk about? It's both.
Yeah, because we have to pay attention to the absolute value of k, or we have to pay attention to the sign of k and or m in the residue that we did, don't we? Like down here, because we wanted the absolute values on these, maybe.
do we? Or where'd it come from in this part?
Actually, didn't they say that if you have cosine of... No, they said if you had cosine of kx, you replaced it with e to the ikx, didn't they? E to the ikz.
Oh, maybe. Okay, what Slim is saying, I think if cosine, or if k or m were negative, because of cosine being even, you could just make them positive and then solve the problem the exact way that we did. So I think we can argue that it's always positive. That's why you can just put the absolute value bars. They made an argument at one point in one of these problems that sine is odd in whatever constant they had. But here cosine is even in the constants that we have. So we can always just make them positive because cosine is even. Like I'm basically saying that like cosine of minus kx is equal to cosine of kx. So I think we're justified in saying only the absolute value. Like, that's how we would get an absolute value. So we put absolute value bars on as soon as we go to ease instead. I feel like we're winning color cone, yeah. That's kind of weird that you can just like do that, but I think that's how you sell it.
Okay.
Yeah, okay, there's
Oh, and then
too many K's and M's in the other part,
I
but
know they're everywhere.
I just fixed in the main work and the rest can just be slightly wrong. Okay, so that's part A. Part B, like K equals 2, M equals 0. To deduce that, we probably need a double angle then.
Oh yeah, cosine of 2x. What's that?
Like 1 minus sine squared or something. Or 2 sine squared or something.
Cos squared minus sine squared, isn't it?
Yeah, I don't think that's one we want though.
2 cosine squared minus 1. That's a good way to do it.
I think 1
Or
minus
1,
2
1
sine
minus
squared.
2 sine squared. Okay. Oh yeah, because then we minus 1 from it.
Yeah.
Oh, and the negative comes over. Yeah. Okay. I think it works.
2x minus 1 over
Where'd
x
that 2
squared.
go?
Dx. Yeah, it's the 2. I don't know what's going to happen with that. Uh, 1 minus sine squared. 2 sine squared.
Okay, I think I see it. Yeah. Yeah, now use the right-hand side of our answer.
Oh, because K is 2. Aha.
Yeah. Yeah. And the minus 2's cancel, right? Yeah, cool.
Yeah. Noish. We did pretty well at that one, I think.
Yeah, it felt pretty good.
Okay, so I chose one other one from the section, number 4. I think it's just one because it's a rectangular one instead.
Okay.
Oh, they're making us find the zeros of sinh, I guess. Oh.
With an appropriate indentation. Well, there's a 0 at 0, isn't there? So that's probably where we need to
Isn't
do
that
a
the
dent.
only 0? Yeah. Because sinh isn't periodic, right? It's just... It looks a little like arctan, I think, or tangent.
Yeah, but what about when you go to complex? Is it?
Oh. I don't remember exactly how the definition looks. E to the z minus e to the minus z over 2.
So it's 0 when e to the z is its own reciprocal.
No, okay, I think even in complex numbers, z equals 0 is the only thing that solves that equation there. Oh, wait. Branch cuts. 2 pi? Like, oh, we have to worry about pies. That's it.
Is that what it is? Multiples of pi?
E to the 2 pi I k is the issue. It's not just e to the 0. So the modulus is just 1, so we don't have to worry about that. We just get oh, it's just 2 pi I times k. So we have zeros at pi I k. Every integer, so on the imaginary axis. That makes sense. Because sine has zeros on the real axis at every multiple of pi.
Yeah.
So sinh being on the imaginary axis, that makes complete sense. Okay. I'm going to assume these are all order 1. I remember there being an argument about how you can find that with Taylor series. Actually, we did a similar calculation, I think in the last meeting too.
It feels familiar.
Okay, so we have a pull at 0 and every integer multiple of pi.
Now I see something here.
Mm-hmm.
This k, because they didn't give us sinh, they give us sinh of kx.
Oh, I forgot the k.
So what does that mean? We've got 2kz. Is that
this is the wrong, I shouldn't have used k there. M. Ugh. I think we're just gonna end up dividing out a k.
Yeah,
I should have.
because I noticed that
Yeah.
they put the corners of the rectangle at like I pi over k. So I bet you that's like right before it hits another 0 or something.
Um. 1 over 2k, I m over k. Okay. Nobody's here. I'm using a Huion tablet. I think it's called like an Inspire or something. Okay.
Yeah, so they're doing a rectangle like here, maybe.
The rectangle is, I think, like up and down. They're like the. I think it's more like that. Or is it?
I'm not sure. Plus minus r would be real numbers, probably.
Oh. No, yeah, you're right. Plus or minus.
Yeah, probably like this, and they're probably
Yeah, they're
gonna
only
like
going
have the
upwards.
little. They're probably gonna cut it out like that, like a razor blade shape or something.
Yeah. Um, K is just a real number, not 0. So it could also go downwards if we chose a negative K.
Okay. Yep.
But yeah, I guess it'll be easier if we choose just the possible one. We could make the rectangle arbitrarily high because we can just make K very small.
Yeah, I like that. Oh, and they're throwing an absolute value K in the answer again. So yeah, they want us to pay attention to the sign of K.
Yeah. So
Well,
minus.
actually, since KX, isn't that if K was negative, couldn't you just factor out the negative?
Yeah.
Okay, cool.
And so I think this is like what they did there is like a proxy for including a sign of K factor, I guess. Or like it
Yeah.
accomplishes the same thing. Um,
Oh, I see. You went up past a couple more. Isn't that too far? Oh, we don't have to go up that far, do we?
or can we go as high as we want? Like this rectangle could be infinitely
Well,
long if we choose a small enough K.
well, we can't choose K. I mean, K is given to us in the shine, right? Or cinch KX. Like they tell us what K is,
Yeah, but if
and
they told us
then
like K is 0.0001, we get a really tall rectangle.
well, yeah, but look down here what you got for Z, right? So M has to be an integer in down here.
Mm-hmm.
So pi over K times our integer. That tells us like how many of those zeros we've gotten to. So right, so in your picture like this, M here would be M equals 1 right here. Is that right? And M equals 2 right here.
Yeah.
Yeah, and so they told us R is plus. They told us go to R plus minus I pi K. So they only want us to go to
Oh,
the first one, I think.
but aren't we going to intersect? Ooh. We're going to cross over the singularity exactly, though, and that's bad.
Well, couldn't we
Oh,
just
we do it cut out. Yeah, okay.
yeah.
Okay, that feels... Oh, no. I erased a little bit too much. I guess we don't really need that upper one there.
Yeah, that's why I said like a razor blade shape. You've seen like the old razor blades?
Yeah.
Yeah.
I get it now. Okay.
Or a bow tie, maybe it looks like a bow tie.
I guess I was getting excited about having an infinite rectangle, but that's just not what we have. um,
That infinite rectangle was making me scared.
okay, so I guess maybe the lower curve can be C epsilon 1, upper curve C epsilon 2. I don't really know what to call all the other bits. Maybe just number them 1, 2, 3, 4, 5.
Wow, six line segments and 2 semicircles.
Yeah.
They did one like that in the chapter, didn't they? It had all these integral signs.
Probably. Oh, This is another even function from 0 to infinity. So we have two odd functions divided.
Oh yeah.
So we're gonna have to do the same thing, especially with this contour that we're drawing here. We definitely have to make it minus infinity to infinity.
Yeah. Okay. Oh, this looks like the cover of the Stewart calculus textbook.
Oh, I think so. Yeah, I think I know what you're talking about.
It's like the hole cut into a violin or whatever, isn't it? Something like that.
I think. Okay, I guess we're now going to get a metric crapload of integrals here. Uh, ooh, so when we have sinh, do we consider e to the kz, I guess? Instead of ikz? That's probably why your other thing was nearly right, because it, like, sinh of iz equals sine of z or something like that.
Hmm.
And then I assume we kind of want to, like, C1 and C2 can probably go together. Actually, those are just C1 goes from minus r to epsilon 1. Epsilon 1 to r of x over e to the kx. Hopefully that's just the e to the kx part feels a little bit weird. I just want to. Okay, yeah. And then C4 and C5 we can group together.
Oh.
So here z, for this one I took z equal to x, but this one z is equal to x plus I over k?
K. Yeah. That must have been chosen so they go to 0 somehow.
Probably. And so only x is varying. So for C4, x is going from r to epsilon 2. Then from epsilon 2 minus epsilon 2 to minus r. Did I do the minus signs on the other one? I forgot it for
No.
C1. There we go. I'm going to get x plus I pi over k. E to the kx plus I pi over k. That's not really going to simplify if we go to sines and cosines. When k is a real number, so. I guess I'll just say e to the I pi over k, because that's a constant now. E to the kx dx. And then we have the two vertical sides, which I guess I'll do independently. So then for C3, Z is equal to R plus IY. And Y varies. That looks like a K. Y varies from 0 to I pi over K. And then R plus IY over e to the R, e to the... Ooh, I'm forgetting... Ugh. It's e to the kz. So it's e to the k x plus I pi over k. So that actually is going to simplify. E to the I pi is -1. Okay, that's much nicer. Then I'm going to make a subtraction for that integral then. Ugh. This is a journey.
How does e to the kz get us back to sinh kz? Sinh kx.
Maybe I should have questioned that more closely.
I remember when it was sine and cosine, they said use exponentials. And I mean, I know you can define the hyperbolic functions in terms of exponentials.
Yeah, I mean, the real answer is I was just guessing. Is there an equivalent for an Euler's identity with sinh and cosh?
Maybe we should have just used sinh kz. Does that work?
We could convert it to sine.
Oh, yeah,
and then
you
use
said
with the regular e.
Yeah, how do you do that? You divide it by I or something? Yeah, you're right. We could have done
Sine
that.
iz over yeah. Okay, I think dang it. Okay. Sinh of z.
Well, most of this doesn't change, right? I mean, all the setup is still the same.
Sine of iz over I. I guess we can rationalize that. Okay, so well, it's sine of iz. Does that matter?
No, wait a sec. Yeah, so if it's sine of iz, that would be e to the I times iz, wouldn't it? Would it? So that would be... Damn it.
We're getting back to the kz.
Yeah, I know. Maybe it'll just work.
Is this an odd number? Oh, but it's not. But even if it was, they wouldn't say. They don't get the actual solution. They just give the answer. Yeah, they didn't do an example with hyperbolics. So wait, what's the relationship with cosine iz is just equal to cosh? We should be able to shuffle around Euler's formula, right? This is important for taking
Yeah.
a real or imaginary part. Should I be doing the other direction of the formulas though? I don't know. So E. Well, this is even more annoying because what it needs only for a real number. Freaking hyperbolics, man.
Yep.
Contour. I'm just gonna go to Google. Hyperbolic functions. If I could just see someone saying to use e to the z, I would be satisfied. Oh, this person is keeping it with Kosh. I think maybe we keep it. Maybe we weren't supposed to bring exponentials into this. How would that?
Yeah, maybe not.
Maybe that'll. Yeah. I hope it'll be okay. I'm gonna change these all to cinches, I guess. Or cinch K. X. Oop. Okay, so cinch of K times that kx plus I pi. I think there'll be some kind of identity we can use for that. Oh, you know what? C3 and C6 can be grouped, I want to say. No, because the R is different. Never mind. Okay, and then just one more integral. From I pi over k to 0, this is C6. The same thing, but the R is negative. Okay. What do I do with this monstrosity?
Just hope a lot of it goes to 0.
Oh, I didn't fix the first one. So yeah, so the bit we're actually interested in is C1 and C2. Everything else we
Yeah,
gotta
that's
find a value.
yeah.
Okay, well, I guess for the two circles with epsilon 1 and epsilon 2, we're gonna want that first theorem with the part A and part B.
Mm-hmm. I feel like we'll need a residue.
Uh, yeah, I'm going to just go with the pole being simple to make life easier. um, so we need the residue at 0 and at I pi over k. So the residue of z sinh kz at 0 is equal to z over cosh kz, and that works out for z equals 0. We don't divide by 0.
Yeah, 0, right? Okay, good.
It is I
What's our
pi
other
over k.
I pi over k?
Okay.
So what's cosh of I pi?
Uh,
I don't know all these things. You
well,
said
cosh
cosh
of
of
I pi is
ix
going to
is
be, it's something with cosine. We can figure it out.
cosine. So it's cosine pi, isn't it? So it's -1. Ah, but we need to plug that in the top too.
I'm just worried that there's another I in front or something. So cosh of iz is equal to cos of z. So you were correct. We can just get rid of the I.
Okay.
So minus I pi over k.
Does that look good? Oh, we got pi squared over 4k times k. Oh, right, because we have to multiply this residue times pi I, don't we? We are going to get a
Yes.
pi squared.
Okay, so we get a contribution from the epsilon 2. Okay, where am I? Ugh, I need to move some stuff around. Jason. Nice. Yeah, this is pretty advanced stuff, so if you're not there yet, it's okay. Glad to hear you're making progress. Okay, that integral gives us 0. This integral gives us I pi times the residue of minus I pi over k.
How are we going to get the other k there?
Who knows?
Yeah, who knows?
Not me. Okay, now we need to deal with, well, no, C1 and C2 are the one we're interested in, so we skip 4. Ooh, I fixed the sign on this, and I should unfix the sign. It's just back to plus. Okay, C4 and C5. Um,
Maybe there's an identity for sinh of a plus b here. Yeah, because I feel like the sinh of I pi might be 0. Or it might, or something will be 0, right?
Probably, yeah. Okay, got it. Sinh, cosh, sinh. Oh, that's really simple. Okay, so I mean, this is gonna get. Maybe I'm just gonna come down next to the residues and say sinh kx plus I pi is equal to sinh kx cosh I pi, which we already said was -1. Just making sure, then plus cosh kx sinh I pi, which should be 0. And so we're just going to get minus sinh kx, I think.
Okay.
That makes this integral slightly less annoying, I think. I don't even know if it does that, to be honest.
Yeah, what's the trick to, why does this, this 4 and 5 should go to 0, shouldn't it? But how? Oh, no. Wait, no.
this integral doesn't seem easy. It seems like like if we wanted to go to 0, we should probably try to bound it. I don't know what a good bound is. Cinch is a well, It's like I remember with sine, they were a big fan of using like that line there as a lower bound. With sinh, we could draw a similar line, but I think it would give us the wrong. It would be an upper bound. Oops. And we'd, since sinh is being divided, we'd want a lower bound.
Can we break it into x over sinh and then I pi k over sinh?
I was wondering about
Pi
that. I guess one of them would turn into a hyperbolic cosecant. I don't know what that integrates to.
There's some way to use the symmetry, like x over sinh is even, isn't it? Oh.
They didn't give us
It's
theorems
even,
for a
so
straight line.
it's another rectangle kicking my butt. I don't even see how we're going to get pi squared over 4k squared, basically. Again, this whole thing should be 0, right? The sum of all 8 of these integrals should be 0.
Yes.
Hmm.
Example where they use a rectangle, I don't see them ever addressing these straight line parts.
Yeah, what happened? Did they all just go to 0 there?
I think so, but they never justify that.
It says the integrals along the sides vanish.
But then they go straight to doing the circular arcs, and then they go straight to the answer without ever addressing the top and bottom.
Really?
That's so annoying.
Where are the top and bottom in that string of integrals there? Oh,
This one right here is the top.
the r's and the epsilons, right?
Yeah.
Is there some way they can take the top and bottom and like just cancel that out?
Maybe. Also, okay, I think they're relying on work from a different example problem in 4.2.
Wait a sec.
Hmm?
Wait a sec. Wait a sec. We're integrating x over sinh kx,
Yep.
right? So there's no mention of y in that integral.
Right.
So if we across the top and bottom of our contour, is it fair game for us just to treat those as real? It doesn't really feel like fair game.
They are oriented different.
Yeah,
like in
so
opposite
like whatever they
directions.
are, they cancel. Well, wait, that's not going to work because we want the bottom to not cancel, right? That's what we're trying to solve for. Oh,
But
damn it,
we
I
did
don't
already
know.
get some contribution from one of the arcs. It's not the right one, but
Yeah, I don't want to cancel the little circular arcs, but I was trying to cancel the flat parts, horizontal parts, but I don't think that's legit because then we won't have any. We won't be able to go from 0 to infinity at all anymore. So they can't cancel. Oh boy.
oh wait, you know what? The integral on the bottom is the one that we're interested in. That's one that we want to solve for.
Yeah.
So
Yeah, that's why I abandoned my idea of
okay.
trying to cancel them because we need it. We can't cancel it.
But we can group them together if we can be clever enough.
Yeah.
Uh
So you're saying they should be equal to each other, and it's like instead of canceling, they add together.
actually I'm concerned they're gonna cancel to 0 because we get minus cinch.
Hmm.
Uh like where I was going in my mind was to split up the numerator like you were talking about before, and then hopefully
Yeah.
notice that um like the left part could be added to the other integral and we just group the stuff we don't know how to evaluate. We would still have to deal with oh, and you know what, they don't cancel because of the orientation of the contours. We still have to deal. Okay, yeah, I think that's okay. Um okay, so we we already, and you know, I think I'm supposed to make these epsilons the same, to be honest, to really justify it. But basically we said that the thing in the denominator is equal to negative sinh kx.
Yeah.
So you know what? We would get a minus sign out front, but then uh, the contour is pointing to the left, and so we could reverse that orientation and put a negative sign in front. So it's going to flip back to being positive. So we could justify doing 2 times. This isn't justified perfectly, but I think it should work if we say the epsilons are the same.
Okay.
X over sinh kx dx, but the catch is we still have the I pi over k part, which I'm not a fan of. I guess it's minus sinh of just kx. is that like how would we write the C4 or C1 like C1, C2, C4, C5, that set of integrals there.
Okay. Tell me, why is this a minus? Because you were playing some trick with double negating this stuff somehow.
So the minus is just from doing the addition identity on the cinch.
Oh, yeah.
And then
So
I didn't
okay.
reverse
So
the
this was negatives. Yeah.
yeah, and then I did not reverse the orientation of the contour, so it stayed as a minus.
Okay.
So does hyperbolic cosecant have a clean integral?
Oh God, I don't know. It'd be log of c
log of
cosecant plus cotangent or something, isn't it?
Log of hyperbolic cotangent x over 2. I mean, that's a lot better than I was thinking it would be.
Yeah, you know what? I'm losing hope in this question.
I'm losing hope too.
I'm losing hope in this question.
I think this is going to work out though. I have faith.
Okay, let's try it.
I'm really lost in the work. Okay. So the entire string of things is equal to 0.
Yep.
This integral will give us a k squared though. The log hyperbolic tangent. Okay, the work is gonna get even messier than before. Maybe what's the deal with C6?
Yeah, C3 and C6.
Oh yeah, we didn't deal with C3 either.
Because we're letting R go to infinity, so what does that do? Okay, so
Well, cinch
K
is
times
faster than
R.
line than linear. Sorry, what?
So K and R are both real numbers.
Yeah.
So yeah, somehow we can bound these denominators, can't we? Or we can show the denominators are, what do we want? We want the denominators to get big to get rid of this.
Yeah, I think we want them to just go to 0. We don't want their help, right?
Yeah.
For the sake of time, do you just want to say that they're 0 and see what we get?
Yeah.
Okay.
Yeah, sure.
Yeah,
I'm happy. I want these to be 0.
Okay. So I'm gonna I guess all the way down below our work, I'm gonna start to rewrite or like where things stand now. Pi squared. It's too big. Pi squared over k plus. I guess I can just.
Oh yeah, I noticed that the other day. You got to be careful with Excalidraw because Mouse and I were doing something, and I noticed that by the time we got to the bottom of the page, we zoomed in all the way, and so like if you went back to the top, the text was like tiny, and as you scrolled down, it just got bigger and bigger and bigger and bigger as you went until at the bottom it was massive. So you got to be careful not to accidentally zoom in as you go.
Okay.
Somehow you managed to never make that mistake.
I only ever write on 100% percent zoom. I'll zoom out to look around, but I would zoom back in.
Well, that's a good idea. How do you get back to 100%?
I just click on the percent itself, and it resets your zoom.
Oh, right in the middle. Yeah, I see. Good to know.
So I do a U sub on this, which gets me an extra factor of K out front. Hyperbolic tangent. Kx over 2.
Oh, you got a K squared.
Yes.
We want that.
So I'll just do that as an indefinite integral. I guess we're going to have to figure out how log of hyperbolic tangent behaves. Desmos. Ooh. That's a function. That's not the behavior that I was hoping for. Because we want to plug in epsilons and r's. One one's going to 0, the other one's going to infinity.
Hmm.
I was hoping one of these would go to 1, and then the other thing would go to 0. Yeah, this is just the last piece of the puzzle here. Like, well, I mean, the lack of k squared on the bottom, I'm not quite sure about for the residue part, but
Hmm.
oh wait, did I just? No, I didn't. Um, yeah, it just doesn't converge. So there's a mistake.
Something's wrong. I feel like our razor blade shape was right.
Yeah.
It was the hyperbolic thing that killed me.
Same. Dang, I was really into this problem too. I don't really know what went wrong.
It's a cool problem, but it's hard. You got any other ones we could queue up?
Yeah, from the next section, we could look at, we just look at one and call it a meeting, maybe. Um,
A unit circle centered at the origin. Nice.
this one just seemed like a bit more of a discussion. Or no, just like a little bit more like a, not discussion, but like maybe just a nice little like investigation. Verify the
Yeah.
argument principle, because each line functions for C is a contour unit to be, where the contour C is a unit circle centered at the origin. Z is a positive or negative integer. I guess that's going to work out. And so do we? I guess we need to actually set up these integrals and evaluate them.
Yeah.
So f prime z is n z to the n minus 1 over z to the n dz. Hey, so I'm well. How about you? And so we're gonna get n over 2 pi I log just c, not absolute value. Evaluate around the contour. And so if we evaluate log z around the unit circle, we just get 2 pi I, right? Because of the branch cut stuff.
Yep.
So we get just n. Does that make sense for an answer? Yeah, because if we have z squared, we get 2 laps around the unit circle, right?
Yeah.
So what about negative n's? Should this be the absolute value? Oh wait, oh no, okay, we expect to get n because that's the number of, like, z to the n has 1 0 with multiplicity n at z equals 0. Or I guess instead of the argument thing also works, but I'm thinking about like n minus p. So in the case of positive n, that all comes from the zeros. In the case of negative n, that's from the strength of the pole. And it'd be a negative number.
Oh, yeah, because as you go from positive to negative, you go from zeros to poles. Yeah, makes sense.
Okay.
Yeah, so if n is positive, then this just tells us how it's a zero, an nth order zero, basically. But if n is negative, we could think of this negative n as basically it would be p in that formula.
Mm-hmm. Okay, neat.
Yeah, that's cool. E to the z.
This one.
Oh, we get.
Yeah, we're just integrating 1.
Okay.
Stupid question. This is 2 pi I? If you integrate just the unit circle?
Yeah, wait a second. What is
Or is it
this?
just 2 pi? But there has to be an I in here, right?
For on the unit circle, we can call z e to the I theta. So dz is I e to the I theta. When you integrate that, d theta, I e to the I theta d theta. Wait a second. Or do we get 0? Don't we get 0?
Actually, 0 is better. There shouldn't be any poles or zeros, right?
Yeah, that is better, isn't it? Because e to the z is what? Entire, but it doesn't have any zeros or poles.
Yeah. Maybe a pull out
Okay.
infinity or something weird, but...
Oh no, hyperbolic cotan.
Oh, I didn't even see that one. It got snuck in there. There should be a cancellation, hopefully, maybe. Freaking cotangent. And hyperbolic. Like, that's the worst of both worlds.
I know.
Okay.
It's like sad face.
Does anyone in the universe know the derivative of hyperbolic cotangent? Ugh. I guess minus hyperbolic cosecant squared is the familiar. Minus CSCH squared. Oh, we get a chain rule. You put a brownie face? Like a crying face? I agree with that. The 4 pi z is really curious too. I assume we'll find out why that is there. Okay, hopefully we get a cancellation. That's what I'm depending on here. 1 over sinh squared. Cosh. Well, over cosh over sinh. So minus, well, actually it could be plus if we rationalize. Just positive 2 in front. Integral around c. I'm saying we get 1 over sinh cosh.
Yeah. Is there still an I in here?
I rationalized to get rid of the negative sign with there. Oh wait, there is an I though still. Thank you.
Now, how do we integrate this? U sub?
I don't.
That doesn't
A
work.
U sub wouldn't work. We need the cosh on top or something. Is there an identity?
Is this?
Like a product to sum?
Isn't this a double angle again? And then 1 over sinh is hyperbolic cosecant. Oh Lord. We should be doing a reading group on conic sections. Honest to God. I could just use
we need it. Yeah.
Just nothing but conic sections. Drill it for 6 months.
Okay, yeah. The same double angle is true with hyperbolics for sine 2x. I lost it. Where was it? There it is. So we have the angle is going to get doubled in our situation, and we'll have a 1/2 out front. Okay. This is another. Is this the? Yeah, the integral 1 over sinh.
This is kind of like where we got stuck in the other problem, isn't it?
Yeah. Let's see if the log tan answer. Well, we have to integrate around a circle.
There's some trick that we're missing.
Residues?
Maybe.
In the unit circle. Oh wait, it's 8 pi z. It's the unit circle. Sinh has zeros on the imaginary axis. We can do this. E to the 8 pi z minus e to the minus 8 pi z over 2 equals 0. E to the 16 pi z minus 1 equals 0. 16 pi z is equal to 2 pi I times some integer m. Z is equal to im over 8. Oh, what the hell is this? I want to rage quit this one and go on to part D.
Yeah, okay. Sounds good. Yeah, let's do D. I like rational functions.
Okay, they're much nicer. Maybe we're just supposed to go to polar form or something and use the series. P of z over q of z, or p and q are polynomials of degree n and m, have all their zeros inside C.
Okay. So, quotient rule?
Oh. I guess so.
Yeah, let's try quotient rule. And then maybe something will simplify.
So we have p over q, low d high. So p prime q minus pq prime over q squared over p over q.
Okay.
P prime q minus pq prime over pq.
Oh, that's cool. We can split it into 2 fractions.
Oh, good idea. Because then in the first fraction, we get just p prime over p. Second fraction, q prime over q. So that's going to be another log.
Nice.
Well, it'll be 2 logs. So what if we're going to get double?
Wait, I think there's a minus in the middle.
True. So maybe we're going to get 0. No. It depends on the number. They have n and m, right?
Oh, you're saying we can like go by cases now. Like this is
Well, if p has
like basically we could distribute this to each one and use the argument principle 2 times inside this problem.
yeah.
Oh, cool.
So
What happened? P was order n and Q was order m.
yeah, I'm trying to figure out the exact argument from this point. We get logs though. Um
And have all their zeros inside C.
yeah.
I guess it's kind of cheating to use the argument principle inside the problem if we're trying to verify it.
Right. Sorry, I'm not using the argument principle. I'm just doing integration at this point.
Yeah. Yeah.
Uh well, I have a feeling these are just counting the zeros of P and Q.
Yeah, it feels that way.
Because log of P and log of Q are both analytic
Yeah.
functions around closed contours.
Yeah, they're polynomials, right? So you could write P in factored form as like, Z minus Z1, Z minus Z2, Z minus up to
Oh,
Z minus Zn. And then you could bring the log through all of that business.
okay. Hey, Zappin.
And how does that help us? And basically each one of those gives us 2 pi I, doesn't it? Because it's like because each one of those is a pole. Sorry, a zero. They're not poles, they're zeros.
It's like crossing the branch cut is how we're counting it.
Oh, because every single one of those things needs a branch cut coming out of it, doesn't it?
Mm-hmm. And so, okay, so if you do factor it like that, we're circling around each one of those, well, yeah, okay, yeah, each one of those contributes to pi I because they both cross the branch cut once, I think. Like, I just basically want to get to n minus m here. And I think the argument that you said, we could probably do that.
I feel like each one does give us two pi I because it's like each one of them has a Pac-Man face that has an overbite of two pi I or whatever.
Yeah.
Does that sound right?
I don't know if it's, well, we don't necessarily need like the Pac-Man thing exactly, but
right. We don't. Yeah, but I'm just thinking of it based on the branch cut idea. Yeah.
But yeah,
But we don't need
they
the
each
Pac-Man
cross the branch
we
cut
don't need
once,
the
I
Pac-Man
think.
body because we're not going out to infinity or whatever.
Yeah. Yeah, I think that's what we get.
Now let's see. So does that make sense? N minus M.
For
Oh,
dividing
because
out Q, yeah.
yeah, because the zeros of Q turn into poles, don't they? Oh, that's lovely. I get it.
Oh, yeah,
Yeah,
that
so
makes
the
sense.
zeros, so that's why it's minus M, because it's like those became poles.
Yeah.
Oh, that's kind of satisfying.
Okay.
Oh, and then they're doing e to the 1 over z. Doesn't that mean you got to go to infinity?
Uh,
Why is
mm,
that making me think of like the point at infinity?
maybe because of the 1 over z is like inversion, but
Hmm.
so the argument principle requires it to be a meromorphic function. E to the 1 over z isn't, so I think they want us to find out what goes wrong.
You cut out a little then. What'd
Oh,
you say? You said
sorry.
it's not meromorphic, right?
Right. And so I think they want us to figure out what goes wrong.
Uh,
I mean, our if it's we should still be able to use our normal like what's the derivative of e to the 1 over z? Like that should we can still find that. Minus e to the 1 over z over z
minus 1
squared.
over z squared. Yeah.
1 over z dz. Okay. Over 2 pi I 1 over z squared dz. Which we could calculate that with like residues, probably. Like I feel like I should just like be able to look at this and know what it's going to give us when it's the unit circle, but I don't.
Doesn't that go to 0?
We're encircling a singularity. I want the formula with fees. Oh, maybe we do get 0.
Yeah, because the residue of this would be 0.
Yeah, okay. I believe 0 then.
Wait a second.
And so then I think we should break, but we definitely have, well, it's not necessarily a pole at 0, but we definitely have a singularity at 0, I think is the point they want to make. Hmm.
So it basically just doesn't satisfy the conditions of the theorem, right?
Yeah, and it's hoping to find, like, evaluate the left side and find a different right side. But it doesn't really, like, there's no poles to count because it's just a singularity rather than, like, I feel like a pole is a specific thing. It's a type of singularity that e to the 1 over z doesn't have. What about the change in argument of f of z?
Yeah.
E to the 1 over z. I want to say that we would get like negative 2 pi I. I can't really justify it though. Maybe that's just what 1 over z would be. I don't know. I wish I found a better way to break this, but I like a like very clear way to get a different right hand side. I just don't really know how to think about the right hand side when it's not meromorphic, I guess.
Yeah. It also had something to do with the winding number, didn't it?
Yeah, that's what I was trying to figure out. Basically, like what the winding number of e to the 1 over z would be. I don't know how to think about that though.
What are we trying to imagine? We're trying to imagine if z goes around the unit circle, what does e to the 1 over z do? Is that what we're trying to do?
Mm-hmm. Yeah. So I was trying to split it up into like polar form or like x plus iy in my head.
Well, when you're on the unit circle, 1 over z is just negative z, isn't it? Is it?
In the unit circle.
Yeah, because z is r e to the I theta. So,
well, negative
if
z
you're
is
on
like
the unit circle, it's just e to the I theta.
it's like
And then
the
1 over
angle
z would
gets
be either minus
reflected
I.
down.
Oh, you're right. You're right. It's the conjugate, isn't it? It's not the negative, it's the conjugate.
Yeah.
Well, okay, so, but still, if we went clockwise along the unit circle, then 1 over z would just go counterclockwise around it, wouldn't it?
1 over z would, right? I don't know how the e to the power of that changes it though.
But then we got e to the power of that. Yeah, what does that do? I don't know what that does.
Me neither. That's where I got stuck.
Well, what if we change it to change z to 1 over t, that trick? Does that help?
Well, the unit circle will be the same, so yeah, I feel like that'd be legit to ask what the winding number of e to the z is, or e to the t, and get the same answer.
Because that's that inversion where like 0 goes to infinity and vice versa.
I still don't know how to get that though.
I don't know how to get it either. I don't know enough stuff about winding numbers yet.
I'm just going to Google. They're giving way too complicated. Or this, I'm not finding anything with like just e to the z. Where do they introduce winding numbers? Winding numbers, they are complicated. They're not that terrible, but they're pretty cool, I think.
So the class you're signed up for in the fall is basically all this stuff.
Yeah. I looked at the syllabus. I don't think they go past chapter 4. I don't remember where they introduce winding numbers. I can't find it.
It's around there somewhere.
Oh, here we go. Zap and I'm starting grad school in a few months. The winding number of the curve C around the point ZJ. Thank you, thank you. Well, that's not, we're not interested in the curve, we're interested in like how the function affects it. Like under a particular like mapping. What was the thing they did with winding numbers here? That's the exact thing that we want to figure out. We're trying to figure out what C tilde is. This isn't helpful.
Well, we could check the answers to the ones we did.
That's true. Well, do we do?
Let's see.
We did number one. Oh, we did 2 number ones, so we can check those answers.
Number one, we don't need to check because.
Oh, the first one. Yeah, they gave us the
it.
answer. We can check this number one though. 4.4.
This was kind of verify as well. Maybe there's not going to be any answers to it.
A is I equals N. B is I equals 0. I think that's what we got. Yep. C is the theorem can't be applied singularity on contour. Oh my god.
Oh god damn it.
We have a singularity. Oh, I figured that out, and then I thought I did something wrong because I got that. I deleted the work.
You did?
I solved for the zeros of sinh of 8 pi z. I didn't say it out loud, but I thought in my head, oh, we're getting a singularity right on the contour. That's weird. I must have done something wrong,
wait
so
a
I deleted
second.
it.
You did do. What'd you get? You got I over 8 and pi over 8 or something.
It was like yeah, I m over 8 or yeah. Oh my god.
Oh, I saw you do that. I didn't know you erased it, but I didn't realize that was right on the contour.
Oh, like what a cheat, dude! Like, I feel like that's wiggling your way out of the question. Like,
Trick question. What? That's an outrage.
yeah, it was a trick. Yeah, they didn't give any sign that it couldn't be applied there. Part D we got right, n minus m. Part E, it just says it can't be applied because of the essential singularity. They didn't do it. Or they're not showing any actual math. Okay, well, we definitely got the idea for E then, at least. We're just taking it too far. Dude.
Yeah, well, we got all the ones right that you could actually do.
Yeah. We were right to be confused about C.
Yeah. All right, well, number 4 from the previous section was difficult. Maybe that's one to come back to another time.
Yeah, I'd like to keep thinking about it.
Yeah, me too.
Frickin' cinch.
But I gotta take a break from it though.
Yeah. We've gone way over time, but that's fine because these were some good problems.
Yeah,
and it's also the last group because I just want to have free time. So,
well, end of an era.
Yeah, thank you so much both for being here for this group and for the general relativity.
Yeah.
It's always nice to have like someone else like bounce off of. So
I don't know what I'm gonna do with all this extra time now. I mean,
number theory.
Yeah, that's true. Number theory is the next thing.
Yeah, I mean, so it's possible I'll like do something during grad school too, but I'm not. Like I want to get there and see how it is first, and then if I have extra time, then I can do something. But
maybe I can convince Slim that we should do a reading group on conic sections.
there you go.
Yeah, I'm not kidding. I'd like to do that if I could find a good book just on conics. I'm sure they're out there.
Yeah, honestly, like, would elliptic integrals be like a good application for knowing those?
I mean, it probably would come up, right? Like hyperbolic stuff, elliptical stuff. I assume all that would come if you could find a good book that did deep dives into conics.
Yeah, I guess I'm just like here's like a cool place where to use that. Although honestly, it feels like the deeper we get into like math and physics, the more they just kind of come up naturally.
Yeah.
What book do you have in mind? I assume for Fembox with conic sections. You're asking that, Slim?
Yeah, I don't have I've never had any books that are just on conics, but yeah. It feels like all the books I've looked at, they just sort of tangentially go into them. But I'm sure back
Yeah,
in the day, I'm sure they had big books that were just fully devoted to conic sections.
probably.
Yeah.
Math books on conic sections. Oh yeah. Elements of analytical geometry. Plane and solid analytic geometry.
What was that one with the red cover that said the universe of conics?
Oh.
I should ask ChatGPT. Yesterday I was at FizzBuzz's stream and he was talking to ChatGPT about which books he should read for learning for doing a speed run of learning combinatorics.
Oh, nice.
Yeah. And he said he was going to shamelessly use ChatGPT and Google search and other tools. And I was like, that's a great idea.
For a speed run, probably, yeah.
Yeah, I want to get behind that.
Oh, it has differential geometry. You're not going to be able to escape from that if you read this book. Oh, these are some crazy Dupin cycles, focal conics, spatial, Steiner's definition, Pascal Pappas, polarities in pencils.
Slim says he had one from his high school.
This book,
Not
I
this
think,
one.
or I assume he meant this one. I don't know. Wow, this goes deep. Spherical
Yeah.
conics? Oh no, and non-Euclidean? Oh no. I never even considered that. That sounds terrible. Oh, elements of analytic geometry. Okay. A spherical conic. That sounds like such a like. It sounds redundant, I guess.
Yeah, it does, doesn't it?
Okay.
All right. Well, if I find a good
Um,
book, I'll let you guys know.
sounds good.
But for now, I got to start reading number theory. I haven't even started yet.
Oh, better get on it.
Yeah, I know. We got a couple chapters to finish up.
All right. Well, good luck with that. Thank you again.
All right, Don. Thanks for having me.
Yep. I'll see you.
Thanks for all the reading groups. Hopefully, there'll be another one at some point.
Hopefully, I really enjoy these. So
Yeah.
yeah. See you.
All right. Yep. See ya.
All right. Well, it's the end of an era. 2 months. It was kind of hectic having two reading groups going on at once. I'm gonna be glad to have a little break from them for a while. I'm gonna start by playing two of these songs. I've just been crazy into both this song and the next one. While that song plays, I'm gonna switch over my info. And Zappin, I saw your question. I just need a minute. Like, this song needs to be in a video game if it isn't already. This feels like it'd be really good, like a really cool, like, vibe. I didn't change my thumbnail on YouTube. Oops. Okay, well, that makes my life easier for not having to change it back, I guess. Hey, Parth. I was going to type up one quick Discord message, and then we'll get back to just, like, doing a normal stream. Okay. Close out. Way too many things open. Okay, so Zappin, thank you for your patience. You want me to rank? It's a very personal thing. I'll tell you how I feel about them. Your experience could be the complete opposite, though. It really depends on the professor, especially. Least to most. No. I'm just separating these out. So we got 4 choices. I'll say 1 is least difficult. Ooh. I like DiffyQ. I feel like DiffyQs, for me at least, are pretty straightforward, so I'd say 1 here. Song is a banger too. Linear algebra is fun, but I'd say for me it's a little bit harder when you have to do proofs. Combinatorics for me is a nightmare. Tensors are probably a nightmare too, but I haven't learned them. So these two are kind of neck and neck for me for the most difficult. It depends what they're doing with the tensors, too. I would hazard a guess that the combinatorics wouldn't be the worst in the world, but tensors are probably really weird. So, yeah. Non-dairy neutrino, thank you so much for the raid. Welcome in, everyone. For anyone who's new here, I'm Don. I do math help streams. I was just doing a reading group on complex analysis. And then we wrapped that up in Yozap and asked us to rank these classes in difficulty. So that's what I was doing. I hope Rashima's good, non-dairy neutrino. Brenner's here on my end. Check him out. He streams about physics and supercomputing. I'll probably get it wrong if I try to repeat everything that I heard him explain on his stream about what he's working on, but basically about how you can manage the memory on your computer more efficiently when doing really difficult like physics computations. It's a really interesting thing. That's pretty much it. Okay. Yeah, no, I I I personally think it's super interesting just trying to like optimize that and compute more efficiently. I don't know like that much about it. I've done some pretty like I've done like an operating systems class and an assembly language class, so I have some idea of how stuff like that works, but I definitely don't know in depth about it. But yeah, thank you again. I appreciate it. If you want to go like rest and raid and run or something, please do as well. Yeah, Zap, and I hope that helps. Like, but really good thing to do is to look up like your professors on rate my professor and get a feel for how difficult the professor is, because that makes a huge difference. I'm gonna just change the playlist. It's one of the things that we're looking at ways to use a ton of computer cores to do a ton of physics, right? Yes, yeah, that was only like one level of what you were doing. Somewhere, yeah, you were also talking about doing like networks of computers all working together on the calculations too, like being scalable, which I guess is the tons of cores. Okay, so once someone else has a math question to ask, I'm probably going to pull some more complex analysis stuff just to study and work on that. And I can pull the question we didn't get to. Oh, Poplo's asking a question. Let me just organize this. Okay, so Poplo over on the YouTube chat is asking, that looks, for a reason that just feels weird. Let me copy paste it in. Why does 0 factorial equal 1? And there might be some deep answer to this question that I'm not aware of, but the way that I think about it is that we all agree that it equals 1 because it's convenient. I mean, there's a better answer than that, which is you could think of it as factorials count the number of ways to order that many things. Yeah, and so basically what non-dairy neutrino is saying. So if you have 0 factorial, there's only one way to order nothing. And so yeah, that works, I guess. But really, we in my brain, I just kind of think that like we all just agree it does because it happens to make all of our formulas work nicely, and you don't have to make a special case for 0, because there's a lot of situations in math where you end up dividing by like n factorial, and you want to let n be like 0, 1, 2, 3. And so the other thing that you might like want to choose for factorial, or for 0 factorial is 0, but then you'll get 1 over 0, and that will break things. So yeah, there isn't a reason for it that I'm completely happy with, but that's just how I think about it. Yeah, Zappin. Magnum, didn't you put that question in chat before? That question seems like a lot of just busy work. Hey, Fizzbuzz. We made the factorial function. Yeah, like that's what I mean by we just say it does. That's how we've like defined it. So Magic, I assume there's some trick to that I'm not aware of, because the only way that I know of how to do that involves just multiplying everything out, and that would be terrible. Um, for those who can't see, it's over in the YouTube chat. I think x to the 6 plus 3x cubed plus 1. They have to evaluate this if x equals 7 plus 4 root 3. And so I don't know how you do that without taking like all day. Why? Because I said so. Yeah. So I assume if you're being asked that question, there's some type of trick, but I just don't know it. So I'm sorry, Mad Yumic, but I don't have a good idea for that question. Probably save a small amount of work if you cancel an x cubed. Like you could say it's like you could evaluate that instead. You'd still have to cube this, which is terrible. And then like figure out what to do with that. Yeah, no, it's not that much less work actually. So yeah, sorry. Oh, Ben, I saw you put a message and then you retracted it. Oh wait, actually I didn't even realize it's on the chat up there still. Well, welcome in, Ben. In the absence of question from chat, we'll look at this one. Can I quickly explain rationalization? Yeah. So I assume that you're maybe first learning about rationalization and you have something that might look like, well, okay, let me start with the most basic version of rationalization because I'm not sure what like math that you're learning, but sometimes in math you end up with a number like 1 divided by the square root of 2. There's nothing actually wrong with this, but for whatever reason, humans or like for whatever reason, students are often made to not have irrational numbers in the denominator. There's no reason why you can't. And so if you have something like the square root of 2 on the bottom, what you can do is called rationalizing the denominator. If we want to get rid of the square root there, what we can do is multiply by root 2 over root 2. And what this does is we get a root 2 on top, but on the bottom, root 2 times root 2 is just 2. So there's no more irrational number in the denominator, and so that's the basic idea of rationalization. Now, it's kind of stupid because if you had 1 over pi, there's nothing you can do to rationalize that. Like, this trick only works with square roots. But for whatever reason, students have to do that. Yeah, exactly. Basically, yeah, like we want to get rid of the irrational thing in the denominator. There's only a clean way to do that when square roots are involved. If it's irrational for a different reason, there's not really a way of accomplishing that. And so yeah, Katab is saying a different situation that's a little bit harder. If you have 1 over 1 plus root 2, you can still get rid of this, but you need to know the trick, which is you take this thing and you make the plus into a minus. So 1 minus root 2 over 1 minus root 2. So on top, you get 1 minus root 2. Oops. On the bottom, you get 1 times 1 is 1. 1 times minus root 2 is minus root 2. Root 2 times 1 is root 2. And then root 2 times minus root 2 is minus 2. And so those two in the middle cancel. That's the idea behind this. So you get 1 minus root 2 over 1 minus 2 is minus 1. So you get root 2 minus 1. So those are the two basic things with how you like would rationalize a denominator. You take the derivative of 1 over x using the quotient rules to get the same answer, taking the expression and making it 1 times x to the minus 1. I bet you can. I never tried it. Just use your calculator. Yeah, that's even easier. I don't know if that does help, Fembox. Would it make life harder? I don't know. Apply algebraic identities to rationalize some places. If you would consider this an identity, sure. I think of it more, it's more of a trick. The calculator thing is about rationalizing. Yeah, so nobody's here. I never tried this, but if you use the quotient rule on this, it should work. I don't see why not. The power rule is much easier, but if we want to use the quotient rule, we'll do low d high, so that's times 0, minus high d low over the bottom squared. Oh, hey, look at that. So we just get -1 on top over x squared. So that does work. And if you thought about it with the product rule, that should also work. It's like 1 times x to the minus 1. Take the derivative of this, which is 0 times x to the minus 1, plus 1 times the derivative. Well, that's kind of circular. I don't think the product rule is a good idea for that, because I'm using the derivative of x minus 1 and doing this part. But if you just plowed through that, you would still get the right answer. It probably wouldn't be considered a valid way of doing it. Fringe 3141, thank you for the follow. You're taking the derivative of 1 and making it 1? Oh no! No, it's gotta be 0. No worries. Hey Fringe, welcome in. This up here, Finbox is noticing 2 plus root 3 squared. And separately, you notice 2 plus root 3 times 2 minus root 3 is 1. D by D1 of 1 equals 1. That's some math I can get behind. There's nothing wrong there. You just keep taking the derivatives. In that case, your 1 is basically like E, I feel like. Your logic is undeniable. So like, I guess you could raise this to a power? Question mark? I'm talking in a high pitch. Okay, let me make room. If I'm gonna really try to cook here, 2 plus or 3 to the 6 plus 3 plus. Now this 1, I'm going to substitute strategically for this to the power of 6. And this is how you're supposed to do it, though. This is stupid. Like, how is anyone supposed to notice this? The differential equation of all circle in a plane? Oh, you can do that, can't you? You know, let me just... Variational optimization, where like the thing you're differentiating by is itself a function. It reminds me of Lagrange's, or like the Lagrange-Euler equation, where you do like the partial derivative with respect to another function. Yeah, like that. Okay. It is kind of like that. So the equation for any circle in a plane, Mashank, I hope I'm saying that right, is x squared plus y squared equals r squared. And so we can take the derivative with respect to x of each side. Um, 1 over 1985 competition problem. Wow. Derivative of the left side is 2x plus 2y dy dx using implicit differentiation. On the right side, r is just a constant, so we get 0. And that's why this applies to all circles, because it doesn't matter what r was. It drops out. And so we can isolate dy by dx to get minus y over x. So I think that's a differential equation that you're after, Mishank. Or they're going to use an example of variational calculus / optimization. Okay, yeah, because I've only kind of just been introduced to it for the weird way this book I was reading was doing general relativity. But I know it gets used for like the brachistochrome curve and stuff like that too. And like all that cool like calculus of variation stuff that you can do if you go deeper into it. I need even more room. Ah. Will you treat dy by dx as a fraction? Why or why not? It depends on the context I'm working in. If I'm doing physics, absolutely, I'll treat that thing like a fraction any day of the week. If I'm doing math, it depends how rigorous the math that I'm doing is. I usually err towards the side of treating it like a fraction. You're not supposed to. But life is easier when you do. And it pretty much works in every situation where you want it to work. Hey, Phobos. Hope you're doing well. Favorite takeaway from the line of thinking is that if you differentiate the kinetic energy of an object, T equals 1/2 mv squared equals 1/2 m dx ct squared, not by time, but by velocity. The momentum P equals mv. Yes! I remember realizing that when I was first taking calculus and physics in high school, and I went to look it up online, and the answer that I saw was just that it's not actually significant and don't read too much into it. And then but that's not really like true. Like I think that there's something there. I can't remember what it is now, but yeah, because because the Euler Lagrange stuff, I think. If of course your calculator's out of batteries, oh no. Is there any situation where it actually doesn't work? Uh, the only trap is if x equals 0. In that case, the last step I did here isn't valid. You'd want to back up a step and go back here. I don't know of any other situations where it wouldn't work. And it's kind of not supposed to work when x equals 0, because if you think about how a circle looks, if x equals 0, it means that you're either here or here, and the tangent line is just vertical there. So it's like you have an infinite slope. So that's where this can break. Okay, from here, I'd like, maybe do I substitute? Well, 3 is 1 plus 1 plus 1, to be fair. Oh man, we could make that convenient form of 3, couldn't we? Or like, what's the dream for that 3? Yeah, nobody's here. You could say like, in the limit, the slope is going to be like unbounded, basically. Yeah, it does kind of work if you think of 1 over 0 as infinity. That's true. Lindsay Lohan told me limit does not exist. What movie did she say that? I can only think of The Parent Trap? Oh, Mean Girls, okay. She was in The Parent Trap, right? I don't know why that's where my mind is going. Like when she was young? Yeah, she was. Mean Girls is a much better... She played both twins, right? Dude, I haven't thought of this movie in so long. Oh my god. Oop. Where'd my pen go? It's right here. Katab, you want to make this... Like, you want to... Well... So I've done that for, like, this step here. Like, you're saying you want to do it here? I'm trying to figure out, like, what this... Like, this should look like a binomial. Or, like, not... Or, like something plus something squared. And I'm trying to figure out what that should be. Like, if you have x cubed plus y cubed squared, what does that look like? X to the 6 plus 2x cubed y cubed plus y to the 6. That's the type of thing that I'm like looking for here. But even then, I don't know if that's going to really help us. Can I explain types of discontinuities in a function? Types of discontinuities of a function. Let me look up a list to make sure I don't forget any. You probably aren't doing essential discontinuities. Removable, jump, and probably asymptotes we want. Okay. You use Pascal's triangle? Oh my god, okay. Probably not figuring that. Oh wait, for how to factor that. Did you do like 1, 2, 2, 1 instead? Or no, that wouldn't work. I don't know. Oh, you're still here, Mad Gimmick. Honestly, it looks like a competition question the more that I look at it. If I can figure out what to do from here, then sure, but don't have faith in me. So, but to answer Nikhil's question, usually when you're first learning about discontinuities, you learn about these three types, and even asymptotes, they aren't truly a discontinuity, but they usually call them that at first. A removable discontinuity is the most general version. I'll just draw it, is just have a normal function, but poke a hole in it at one point. That's a removable discontinuity because you can fill in that hole and just get a clean continuous function. And so the way this comes up the most often is with rational functions. So an example of a function with a removable discontinuity is, say, x minus 1 over x minus 1 times x plus 2. And the thing that should jump out here is that the x minus 1s cancel. And so you could cancel them and say it's equal to 1 over x plus 2. The catch is we're never allowed to let x equal 1. Because of this previous step here, we've already divided by x minus 1. So even though it's nowhere in this next step, we're not allowed to include x equals 1. It's just a weird thing with, being technically correct when it comes to math. And so the way this function would look, it's a left shift, right? Yeah, it's a left shift. Oh my god. So the function will look like this, where it just looks like a normal 1 over x plus 2 function, but we have that little hole cut out right here. It's also relevant to the Cauchy residues. Oh, the removable stuff? Yeah. So when you flashback quantum mechanics exam, where the question is basically, what's p hat to the 57? Where that's a momentum operator. Trick was to notice the particular momentum operator satisfied p hat cubed equals 1. So you have to compute. Oh no. They're just making you do math there. That reminds me of the trick with like I to the 4th equals 1, so you can simplify that. Because that's a removable discontinuity. Katab, you're asking me to explain the heat equation. I only know the basics of it. 3 Blue 1 Brown has a very good video on it that I'll try and find for you. Just explaining intuitively what the heat equation means. There's two parts to it. I'll link the first part. That video will do a better job than I can do. Someone mentioned physics. I mean, does the heat equation count, I guess? Okay, a jump discontinuity. That happens with... Okay, well, yeah, heat. Yeah, okay, fair. Jump discontinuities happen the most often with piecewise functions. I guess they only really... Well, they don't have to be. But you usually see these with piecewise functions. So I'll say f of x, we can go as simple as possible, like equals 0 when x is less than 0, 1 when x is greater than or equal to 0. And how this function looks, actually, I'm going to make that a -1, just to make the graph a little bit clearer. How the graph looks is when x is negative, we just have a horizontal line there. Then when x is positive or 0, we have a horizontal line here. And so right here at 0, it's literally like a jump. So that's why it's called a jump discontinuity, where the function just suddenly changes from one value to the other with no like gradual increasing or decreasing. And the final thing is an asymptote, which honestly this function we talked about before also has an asymptote. An asymptote basically happens when you would divide by 0, but you can't cancel anything. So this function has an asymptote at x equals -2. And I drew the asymptote in here. So I said they're not really discontinuities because the function is never defined there in the first place. I mean, yeah, it's a little bit weird. Like, I've been burned by it before when studying, like, when trying to do certain proofs about discontinuities and considering an asymptote a type of discontinuity. But when you're first learning this, they usually call these discontinuities because the function does kind of jump from one thing to the other. And so around these vertical asymptotes, the function will always like blow up to positive infinity or go down to negative infinity. And yeah, so those are the three like kind of basic types that people usually need to learn about. Magnumec, I don't think I know what to do that question either. Are you just putting like competition questions in here? Because I feel like that's what your questions are, to be honest. And I really don't know how to do them. You watched it, but you didn't understand it. So I think I can solve the heat equation. I don't have a good understanding of what it means. Yeah, but there's other asymptotes where the left and right limits do agree, like 1 over x squared. But yeah, like the way that at least like the in the math sense, like the function is continuous everywhere where it's defined. Well, this one isn't. It's just not defined at x equals -2. Like that's not in the domain that you're talking about. This one, you could definitely point out a discontinuity there at the removable one. I guess that's the difference. No, I had it in my head and now I lost it. That doesn't make sense. There's some way that you can distinguish, or even though the function isn't defined here, there's a mathematical way of explaining the difference between the two things. I guess whether they're finite or not. Yeah, the equation is usually the first thing that you learn about with PDEs. It's the first thing I learned about. Um, but yeah, so I could go through the solution to the heat equation. I can't really tell you what it means though, Kitab. So if it'd be helpful to see the solution, then sure, but what it intuitively means, I can't do a better job than 3 blue 1 brown of saying that. Or even really a different job. I don't understand it well enough to have my own explanation. Something is discontinuous if it is not continuous. If I dig around enough in Zach's Discord, I could find like the exact problem that I got burned by. So I was trying to use 1 over x as an example of a function with a discontinuity, and I could not make the proof work for the life of me. And eventually Zach popped into chat and like told me like, oh, it actually is a continuous function. I don't remember exactly when during the class it happened. Oh, Femox posted his work for the 7 plus 4 square root 3 problem. Come look at that. Okay. Oh, that's how you figured out the square, like the square root of that. Interesting. Oh, okay. This 3 became a root 3 squared. Wow, okay. So then what do you do for the actual problem? You completed the square on the denominator. Okay, and then you canceled. So actually, we got to the same stage there. That's where I'm stuck right now. Like I did it by a different way. Then what do you do? My stomach just growled. I just realized that I'm hungry. uh, so you're figuring out what cross terms are canceling and which ones are adding, basically. Yeah, okay, that's where the Pascal's triangle comes in. All the odd terms cancel because you need that negative sign from there for it to cancel. Huh. So you only have to worry about the ones with an even power. But yeah, I guess that's the hard part done, because once you know what this is, you just add 3 and do 1 over that. Huh. Alright, that's clever. I think about how you get the cancellations there. Equation is most basic sense says how quickly the temperature of an object changes proportional to the difference in temperature between it and the surrounding space. The consequence of this is that all objects in thermal contact will tend to the same temperature. Oh, nice. Third is where you fix your mistake. Oh, I'll copy that over to Katop in the YouTube chat. Even though it is up there in that chat, but just in case it helps to let him like copy paste it. Well, nice work on that, Fembox. Yeah. Get this hyperbolic tangent off my Wolfram Alpha, please. No. Get it away. I just want to... There. I think it's for diffusion material as well, neglecting advection. Oh wait, yeah, so... Diffusion equation. Does it look the same as the heat equation? Oh, Wikipedia's give me the more advanced version. It is identical to heat. Okay, yeah. Neat. Okay, honestly, guys, I think I just randomly realized how hungry I am. I might call it here for the day. In a grander sense, I guess you would just call it diffusion equation because heat diffuses. I guess so, yeah. Yeah, especially like with streaming, my mind is just so focused on like talking to chat and figuring out like what to do next that I forget that I have to go to the bathroom or eat or stuff like that. Yeah. So I think this is a good time to probably just call it. So YouTube stream, I'm just gonna cut that off. Then on Twitch we'll look for a raid. Yeah, exactly. That's what I'm having. People are on YouTube, thanks for being here. I'll be back on YouTube on Thursday.